Hello guys, this is the fastest revision video of thermodynamics and this is only meant for revision purpose. So let's start. Please like, share and subscribe and whatever you want to do with the video. So let's just start. First main thing is that heat and work. So heat and work that are denoted by Q and W are actually path dependent. So these depends on path. So these are path functions, and whereas every other quantity like P, V, T, S, U, H, A, G, these are all point means this to this point. So delta, I will write delta P or delta T or delta U, delta S. These are point functions and this is path functions. Now the next thing is the zeroth law of thermodynamics. So zeroth law tells that C, let's say C, A, B, okay, if A and C are in thermal equilibrium and in B and C are thermal equilibrium, then A and B are also in thermal equilibrium, because obviously the all temperatures are same, so everything is in thermal equilibrium. This is the zeroth law. Conservation of thermal energy. So like this is the thermal equilibrium for zeroth law. The first law says that the total energy is conserved. So what is it? This is Q is equal to U plus W, or del Q is equal to delta U plus del W. Okay, this is the first law. This says that the net energy is conserved, total energy is conserved. Now the second law states that there is the entropy, that is delta S, is delta Q by T, which is always greater than 0 because it is always increasing. Entropy always increases. Okay, we will see that in a while. And third law, the entropy of a universe is always increasing. And third law is that at there is 0 Kelvin, the absolute. So at that motion ceases. Okay, motion ceases or stops. There is no motion. Okay, these are the three laws. Now one main thing is that if this is my system, if heat in is positive, work in is negative. Okay, heat in, putting some heat, that I'm putting some heat. Okay, let's say I'm putting some heat to my pressure cooker, and the pressure cooker is doing cooking, so it is doing some work. So cooking, because I'm obtaining some work, so work obtained is positive, I'm gaining something, while heat input is positive because I'm putting some heat to get some work. This is the whole sign convention, and if heat is out, that means it is negative. This is my system. Okay, next thing is that let's take PV. So we know PV to the power n is constant. I will plot all the curves. This is n is equal to 0. If n is equal to 0, V to the power 0 means 1. P is constant, that is constant pressure. Okay, straight line like this. If n is infinite, then constant volume like this way. If n is 1, then isothermal, PV is constant. Okay, if n is gamma, then adiabatic like this, and NaN, then it is polytropic. Next thing is that let's take first isothermal. In isothermal process, that means T is constant. Okay, T is constant. This means work is minus P dV del work. Okay, integrate. So if this is an ideal gas, then P is nRT by V. We put that. So while putting, we finally get RT nRT ln V2 by V1. This is the work done in for isothermal. Also V2 by V1 is, so we know P2 V2 is P1 V1 for ideal gas. So here V2 by V1 is P1 by P2. In the ln term, we can also write this. Next is adiabatic. Adiabatic means Q is 0. Okay, this means that it is either insulated or the process is so fast that it doesn't have some time to exchange the heat. So let's see W. So this means P raised to power gamma is constant. Okay, so W is under root again P dV. Okay, and instead of this P, write this here, put this. Okay, and get constant by V raised to power gamma, and that way solving all this, okay, we finally get that the work for a closed system, adiabatic, is equal to V1 V1 minus P2 V2. Okay, divided by gamma minus 1 for closed. And for open, work for open system, This is gamma times W of closed. So just multiply gamma. This would be for open system. Okay, for open system, let's discuss. This is my open system. M1 is coming. Okay, M1 is coming. M2 is going out. Open system means mass can go and out, in and out. Okay, and let's say some heat is given in and shaft work is out. So some accumulation M dash due to this heat, something remains, and some M double dash after this goes M2 out. Some mass is still here. Okay, some mass was here. Okay, where the heat works. So overall, let me just tell you. So it would be M1 into the, so H here, small h means that this is H is M into H. Okay, mass into, this is per unit mass. Okay, enthalpy per unit mass. In that way you can see. So H1 plus kinetic energy plus potential energy. Why H1? Why not U1? Because U plus PV we need to take some internal energy plus the flow energy. Okay, internal energy plus flow energy, because it's an open system, so that's why we need to take flow energy also, plus M2 into again this U, this will be U1 plus KEPE. Why? Because here we see that this is in the system itself. M2 no, M dash is already in the system, it's not flowing out. Okay, so M dash plus some heat that is coming in and work shaft is going out. Okay, plus M2 is the final thing that you saw, H2 plus KEPE. Okay, KEPE, this is, and finally the thing that remains accumulated. So U2, I will tell this U dash. Okay, and this is U double dash plus KE plus PE. Kinetic energy is half mv square and potential energy is mgh. So next we have the free expansion. Okay, here what happens if I have this gas content here and and this is vacuum. Okay, and I suddenly remove this, what happened? The gas will go as so fast that the net work will be zero, thermodynamic work. Okay, thermodynamic work would be zero. Why? Because thermodynamic work moves in, is calculated when it is in slow steps, but this is such a fast step that the work would be zero. If it is insulated, Q will be also zero. And then what will happen, sometimes in question is given that half, this part is half, so now the volume would be double in that case. Okay, this way you can see that the volume will be double, the moles would be same. Okay, so that way you can calculate the pressure and all, and the temperature would also remains delta T also remains same. Why? Because nothing is going out in that case. Okay, now let's talk about next thing is in adiabatic we need to remember this is everyone know. Then there is T and V, T V minus gamma, and then there is T and P. This one is very important. So it is gamma minus 1 by gamma. Gamma minus 1 by gamma is constant. This is really important. Okay, next thing is, let me write this U. Okay, four main things: U, H, A, G. U is we know Q minus W. Just write this. Q is TDS. Okay, now delta S, let me tell, entropy is del Q upon T. Okay, this is how entropy is randomness, degree of randomness. If liquid is going to gas, the vapor will occupy more, become more random, so entropy will increase. Okay, so delta is T upon dQ upon T. So TDS is Q. So Q here I will write it as TDS, and W is PdV. Okay, so this is U. Now for H is U. So I will write again U, whatever I got, plus, so it is U plus PV. That means if I take D delta U plus delta PV, delta of whole PV, so it will be PdV plus VdP, because this is PV whole delta, so I just use product rule. Now PdV, so this is TDS plus VdP. Now A is Helmholtz, so this is U minus TS. Okay, and because G is H minus TS. Okay, So here u minus ts, I will write it little bit directly, not too direct, but u is already we know tds minus pdv. Okay, u minus ts, so minus the delta of ts would be the differential, the product rule I will apply again, so it will be tds plus sdt. Okay, so tds this will minus sorry, because here it is minus, so it is also minus, this will cancel out, and this will be minus pdv minus sdt. Okay, and finally h minus ts, h I will write out directly, tds plus vdp minus tds minus sdt, this will cancel out, and g we all know vdp minus sdt. Okay, these are all the four very important, and you can just derive it right away. You just need to know that q is tds and work is pdv, and one more, and these things that u plus pv, and a is u minus ts, and g is h minus ts. Remember just these all things, and you can find out everything as it is. So these are Maxwell relation. These give rise to Maxwell relation. Like if I say for u like we had tds minus pdv, so what happens, take this thing divided by this derivative, take this thing divided by this derivative, interchange them. Okay, with the sign also, like del t upon del v is equal to, minus will come because this is minus p, so minus del p upon del s. Okay, at this would be at constant s. Okay, interchange this now at constant v. This is the first relation of the Maxwell relation. Okay, now one way to remember all the Maxwell relation, either you can just find out that, but one way is to write, remember this tapasvi. Okay, tapasvi in this manner. So what will happen, just write this, let me make 4 block, tapasvi, tpsv. Okay, first is t. Okay, t here, p s v. Okay, first horizontal and t above. Okay, then for this is for the u1. Okay, for h1, first horizontal, t above, horizontal, just remember the position of t, horizontal, then t vertical, tp s v, t vertical, p s v, tapas v. Then we have now now we focus on t down. Okay, t down, that means t down. So now we again take it to be up, because we first go this way, or you can take any way. Okay, just remember, let me just tell you, like this, it is like this, like this, like this, t down, t p s v, t p s v. Here it is going up, here it is going like this. Whenever it is going horizontal, okay, horizontal means this, so just put minus sign, just put minus sign. Okay, when horizontal means this side, so just put minus sign, and that way tpsv, in that case tpsv, here you can get, and just do this equal to, you get. Very simple, nothing to be scared about. Okay, and these are vertical, so in vertical it's not like this, but horizontal there is a minus sign. Okay, now let's see next is let me tell you about okay, cp minus cv is r only for ideal gas. Okay, here you can also find out, and cp by cv is gamma. Okay, this is all you know. Let's move to the three engines. Okay, this is my hot reservoir. This is my first engine, second, third. This C cold reservoir. Okay, from hot to cold, this is Q1, this is Q2. Okay, same ways like here also. I'm not you can write QH QC. Okay, anyways, if work is out, okay, if work is out, this is like my car engine. Okay, so because I move from hot to cold, make it cool and take out some work, so this is my heat engine. This is my heat engine. Okay, where work is coming out, so that is Q1 minus Q2. Okay, this is heat engine. This, let it be my refrigeration. Here I am coming like this. Now let's go opposite, from cool to hot. Okay, from cool to hot, if this was like this, coming work out, now we would have to put work in. Okay, simple. Now this is my refrigeration. Okay, now my aim is same, like if I put again, but now going in the same direction. Here you might feel this might confuse you a lot, like this is also heat pump. This is also the same. So what is the difference between refrigeration and heat pump? In refrigeration, my aim is this, to maintain this C, and in heat pump my aim is to maintain this H, hot reservoir. Maintain cooling, here maintain heating. That's why all these things are done. Now let me write all their equations, the efficiency equations, because they are main. The efficiency and COP. Okay, I will tell you. Efficiency of heat engine is 1 minus T of 2. 2 means cold. Let me write cold, and T of hot. This is the efficiency of heat engine. Everyone knows that. This is 1 minus Q2 by Q1. COP of refrigeration cycle, refrigerator. Okay, this would be TL by, because I need the lower temperature, so this is lower, or TC, whatever you want to say, and TH minus TC. This is the total kind of like, this is Q2 by Q1 minus Q2. This is my net work, and my aim upon the net supplied energy. Again, COP of heat pump, my aim here is to maintain TH, and the supplied work is this. That means QH or Q1 minus Q2. Okay, this is heat pump, refrigeration, and that is heat engine. Okay, so all this are done, and like delta S you can find out directly, like del Q upon T. So if constant volume, NCP delta T, okay, dt, if dt and upon T, so integration, this will put ln T, okay, T1 by T2, that way. Okay, remember that, and let me write this whole expression. Delta S is equal to NCP ln T2 by T1, okay, minus NR. So NCP, this is also way to remember this. However, you can prove this directly, because delta is Q, so Q is U plus PV. Okay, very simple. If U is NCV dt, and PV, if you want V to integrate with P, write like into a V, so write P is equal to nRT by V, that way. Okay, that way it comes up like this. NCP, CP means pressure, so write here pressure. P2 by P1, 2 by 1, 2 by 1. Okay, and this minus, when it is pressure, it is minus nRT, NCP, CP means P. Okay, similarly for volume, NCV, T2 by T1 plus volume, for volume plus nRT, V here ln V, 2 by V1, again 2 by V1. Okay, and finally if I say only P, so NCPV ln P1 by P2, P2 by P1, and plus again NCP, CP and CV ln V2 by V1. Okay, this was delta S. Now one more thing is that 1 ton of refrigeration is 3.51 approximately, I just remember 3.51 kilowatt, 1 ton of refrigeration. Okay, and for throttling process, let me discuss this. Throttling process is like there is a constriction, and here the pressure will decrease. Always through a throttling, pressure will decrease, and the delta H is 0. Okay, net enthalpy is 0, so pressure will decrease in throttling. That is only because this is expansion. So what will happen is that we will make a graph according to mu. Mu is some throttling coefficient, that is delta T upon delta P at constant H, that is isenthalpic and here like this graph would be there of T versus P. This is mu is equal to negative. Why? Because this slope, this is del T upon del P slope is negative, their slope is positive, and this is slope is 0, so mu is 0. Okay, and all these points would be there like this where mu is 0. Okay, like this way. And also we know one thing to just remember is pressure will always decrease, so whatever we want to see, we will move this way. So if mu is negative for that material or the system, and pressure will obviously decrease, so temperature will increase for the system till a point where it becomes maximum, and then it will decrease further. Okay, in that case. So these were the main thing of this. And let me just tell you one more thing, that is the Clausius-Clapeyron equation. So dP upon dt, this is H of fusion. Okay, H of fusion, like the vaporization. Okay, from liquid to vapor. So that H, how much energy is needed here, H of that, HFG, okay, upon Vg minus Vf, okay, into 1 upon T. So this is, I write it delta V, I write it like that, delta G Fg and into T, delta T. One way to remember is this, like T is there, H upon V is kind of like P, because H is U plus PV. So in a way, if you just see this, neglect this U, so H is P upon V is P into V, so P is H upon V. In that case, I'm just telling you a method to remember this in a way. So dP by dt is there, and in throttling also we see dt upon dP. So mostly our pressure and temperature are taken as slow. So dP upon dt, HFG by delta Fg 1 upon T. And when we just integrate and make this, so it is P2 and P1 is HFG, okay, by R 1 minus, this is kind of like the rate, Arrhenius equation, that rate kind of thing only. Okay, this is easy. So this was the whole thing like here. Now let's move to solution thermo. Before that, let me just tell you this beta volume expansivity is minus of, not minus, volume expands. Expansivity means volume is increasing, so not minus, by V into del V upon del T. Volume expansivity means volume we need to take up, because this is our main variable that is changing, so take it up, write down this, and the K, the isothermal compressibility. Now volume is now decreasing, so what we take, this is the here the volume will decrease, so put a minus sign. Volume, this is compressibility, isothermal compressibility, so at constant temperature, volume expansivity at constant pressure. Now let's move to solution thermo. So in solution thermo, I will let me write down the first two main equations. Is like G is equal to dG is V dP minus S dt. Okay, this we know. Pressure and temperature, this, that way we would mostly say at constant pressure and temperature. So dt and dP like this, beyond the minus sign, this we have already taken, and just add summation of Ni into mu I. Okay, xi mu I, if this is like, if it is n, and if we just divide this, then this would divide and xi. If we take this divided by total moles, then this will also n by ni by total moles, so xi would come. Okay, just you can just figure it that way, but ni mu I. Okay, this is the first main equation, and the second main equation is that dg is equal to RT ln F for real gas. These two are really important, and let me just now tell you the final equations, main equations, which are very important. From these two only we get all the things, only these two major equations, and one is that V residual is V minus V real minus, this is residual, this is V real minus V ideal, and one this formula, and also this Z is V, it should be V real V real gas, volume of real gas by V of ideal gas. Okay, because that's why V of ideal gas is RT by P, so it comes like this. Z is compressibility factor. Okay, now let me write the formulas. That is GR means residual. This will be now ln F. Now residual means real minus ideal, so real F divided by ideal P. Okay, F by P we know it is 5 fugacity coefficient. This is also equal to Z minus 1 upon P dP. Okay, from 0 to P, remember the limit 0 to P, and this is V of the residual, V residual by RT dP. This is PV by RT, but this is V residual, remember, not real. 0 to P. This is the first important formula. Second is that ln, if we take FL and FL sat, liquid, F sat. So for liquid, this formula takes place like this: volume of liquid, molar volume of liquid by RT, V by RT into P minus P sat. Third formula, this is for liquid. Okay, liquid, remember. Third is Lewis-Rendall rule. Okay, I'm giving you all these main formula which will help you to crack any question in solution. Okay, Fi, this is some ideal. Lewis-Rendall means the solution. This top, this rooftop means solution. This cap means that is in mixture or solution of ideal is equal to Xi into Fi of pure. Not means pure head. Okay. Fourth is, this is Lewis-Rendall. Also phi ideal is phi I only. Gamma I, very important. The activity coefficient is Fi of real. This is real. So this is Fi real, fugacity of a mixture of a real mixture divided by Fi cap. Okay, cap means that's in the solution of ideal. Real upon ideal. Okay, now this ideal thing can be further used using this. F ideal can be written as this. Putting this, we can put Fi real. Okay, Fi real upon F ideal means Xi into Fi naught of pure. Okay, and this thing Fi by Fi naught, this thing is actually alpha, or we can also write A, activity. So activity of I, this means activity of I divided by Xi. So finally, gamma I is equal to activity I upon Xi is equal to Fi by real. Okay, Fi of so Fi pure into Xi. The next thing is that ln gamma I. Okay, these are the main formulas to remember. Ln gamma I is Ge bar by RT. Now Ge, here it Ge means gives energy. Excess gives energy, that is gives of real minus gives of ideal, and bar here means molar property, partial molar property, which means del upon some property, let's say G, Ng upon del L. Okay, at P, T and different J. So this is the partial molar property. Partial molar property actually means that how, like, if this is water and we make some alcohol, so this will behave differently with water, so it will occupy a different volume and have different molar properties depending on the amount. So that is partial molar quantity, that depending on the amount, and that will actually depend on the interactions between these. So I'm just explaining it in a minute. So this interaction, due to which there is some partial molar property, because it depends on this amount. The molar property depends on the, in the solution, depends on their interaction and the amount. So ln gamma I, okay, gamma is activity coefficient. Okay, this is Ge bar by RT, and this could be actually written like this: N Ge by RT. Okay, this whole term RT is, we are taking it inside because it doesn't matter, and this is by Ni at constant temperature, pressure and different moles. Ni is, let's say, water, and ith is alcohol, then J is water. Okay, in that case. And finally, because this is holds true. This is partial molar property. We also know something called that the total molar property, the molar property is the sum of xi into partial molar property. Okay, this is something we know, and this is this thing. So what we can write, that the total molar property Ge by RT, the partial sign gone. So Ge by RT, that is xi, some, like let's say it's binary, so x1 into Ge bar 1 by RT plus x2 Ge bar 2 by RT, and in this way we can, instead of writing the Ge by RT bar, we can write this ln gamma. So x1 ln gamma 1 plus x2 ln gamma 2. Okay, this is very important, that ln gamma I is Ge by RT. Next thing is that G, what is then Gr by RT? R means this residual property, which means G of real minus G of ideal. Like, and G of excess is also the same, G of real minus G of ideal, real minus ideal. But this is for liquid and this is for gases. So kind of the same thing. And for gases, we know instead of this 5, we have this fugacity coefficient. Instead of activity coefficient, we have fugacity coefficient, and instead of so let me write it, Gr by RT, that is summation of the xi into Gr bar by RT, and instead of this we can write the ln, instead of gamma I, this is not x, this is y, because gas, we can write ln phi I. Next thing, one important thing is that, first thing is that I told you m is summation of xi m I bar. Okay, next thing is that this actually means x1 plus m1 plus x2 m2. Okay, and finally from here only we can get that m1 bar, because if we, this is bar, so m1 bar, if we need bar, so m1 bar is the total, the not the total but the molar property, okay, of the total whole mixture of the real mixture or solution, the total of that minus x. 1 is there, put 2, if 2 is there then down also 2, dx2, and this dm, mm x2 x2, and 1, then it is 2. Now the other way around also, m minus 2, so 1, and this is the same thing. Okay, next thing is Gibbs Duhem says that xi into d. So the change in the partial molar property and this addition of that, like this summation, this would be 0. Okay, so mi bar dxi summation is, this is not 0. This way we can get that this m minus x1 d m by dx1, that way we can get m2 bar. But this, if the differential is with mi bar and this kind of thing is there, then this is 0. This is Gibbs Duhem equation, and we found that this m bar was in that case ln gamma 1, or we can say if it is 1, so because of Ge bar by RT. So we can erase this and we can put x1, let's say binary solution, x1 gamma 1 into d gamma 1 plus x2 d ln gamma 2 is equal to 0. x1 we put d ln gamma 1 is equal to minus x2 d ln gamma 2. We divide both by x1 dx1 and dx1, because x1 plus x2 is 1, so dx1 is minus dx2. We put it over there, here, and the minus dx2, this cancel out, and we finally get this kind of relation. This, if some ln gamma 1 versus x1 is given, so this slope we can take out, and this, using this slope and any x1 quantity, because if we know this slope, and let's say we know x1, we know x2 also, because we know x1, so we can find out this thing. But overall this is the main thing, and the root equation is this, and that ln gamma 1 is equal to Ge by RT bar. Now next thing is one very important equation, that is m. Okay, let me, before writing this whole, let me tell you about the mixing. So delta m mixing, property of mixing, this is equal to the, see, this is a final m, okay, and this is for the final M the mixture, and the individual. So individual components like component 1, that M0 1 and M2 1, individual pair getting mixed. Okay, so how it would be? M, the final that we get, minus the sum of the individual, Mi into Mi naught. Okay, this not means pure. Okay, this is one thing. We can actually put G and other thing, but let me just tell you something, that Me, so the excess property is M real minus M idle. M real minus M idle. If I write real, let's say write real, and if idle mixing, let's write idle. Okay, now substitute this with this, so we get M real. M real we write it M only. Okay, so M real is equal to M excess. This goes, so plus M idle, and M idle is delta M mix idle plus summation xi Mi naught. This equation is really important and contains both these equations. So in one equation we can actually get both these equations. Next, we know that so delta G, so delta H makes is 0. Okay, for idle, and delta V makes idle is also 0. And then we know one more thing, that is delta G makes idle is equal to RT summation xi ln xi, and delta S makes idle is equal to, remember this, that we know G is equal to H minus TS. So H, now delta, all delta, not T, delta here. So mix, right, mix. And if I put idle and idle, we know delta H idle makes idle is 0. So in that case, RT, this is done. So remove the T, add a minus, remove the T, and that is delta X mix. Okay, so these two we get. And then there is Raoult's law. Raoult's law is this. So the total pressure in the vapor is equal to the total vapor, the total pressure in the liquid in that case. So let me write it in this way: phi I for the this part the vapor, this part the liquid, equal to, okay, phi I for vapor we have yi phi I, so we will write gamma I here. Okay, for liquid we have xi, and here the total pressure Pt, and here we write the partial pressure or the vapor pressure actually, vapor pressure. This is Raoult's law, modified Raoult's law. And if it is Henry's law, when x is very less, almost less, x is very less than, let's say 0.5 or something, very less, like even 2, less than even 0.2 or 0.1, when x is almost tending to 0, then what we can take here is Henry's law, which says that this becomes as it is. Instead of this, put xi into some constant, Henry's constant, pi, let's say. Then there is one more thing, that G by RT and differential by T would be like if you put 1 by R, then G, so this apply product rule, just apply product rule, okay, and 1 upon T d of G, and use two equations. First is G is equal to H plus TS, okay, put this over here, and for DG we know it is VdP minus TdS. Okay, putting these two, and we finally get this thing, that dG by RT upon dt, or let's say dt, is equal to, let's not take dt, we find this V by RT, okay, dP minus H by RT square into dt. Now finally, for the chemical reaction equilibrium, we know it is pi means summation, not summation, of product. Okay, capital pi means product of the phi I into to the power mu. Mu is here, it means like a, let me give some example. Let's say NO plus O gives NO2. Okay, then mu here means this is minus 1 because this is 1 Okay, this is let's say half O2. This is also 1. So here this one product side will be plus 1. The coefficient here will be minus half, and here the coefficient will be minus 1. So the total sum of all this is this goes away, and this is minus half. So mu is minus half. Remember this thing that the yi will be ni. Okay, ni for ith compound. Let's say A plus B reaction is going to C, and there is some mu here. Okay, overall A, B, B, C, C, and there is some mu here, and there is an extent of reaction, which means that dn is equal to mu d epsilon. Okay, this the amounts of mole is how the extent multiplied the total. This I will say total of stoichiometric coefficient. Okay, and so this the yi, the mole fraction would be ni plus the stoichiometric coefficient of ith into epsilon upon ni naught, the initial, plus stoichiometric coefficient of the overall into epsilon. So this is the thing, and so here we can write out finally phi I to the power this overall stoichiometric coefficient into y. Let's say if we have, let's take an example of this. See, because then it will be very clear. Otherwise, the formula would be really difficult to follow. So this is phi I to the power mu of different pi is there because of different this thing. Okay, let's say phi I to the power mu. This hardly matters because it finally reduces to 1 in most examples. The yc, so the product will be above the division, and this will be down yc, capital C, ya, yb, yd, right? All these, then to their powers add their coefficients, like this is c, d, a, b, and this would be equal to and this multiplied by pressure, because see, this is the same thing like phi I we did yi into total pressure is xi gamma I p. So this thing is the whole same thing. Okay, but in a just a little bit modified way, like the summation and the above and denominator like this into the pressure, the total pressure to the power mu, again to the power mu, and this also to the power mu, this is also to the power mu, and this is equal to the equilibrium constant, let's say kp. And for yc, let's say I take any example like let's say the same example, half O2 gives NO2. So let's say initially we had N naught will be like 1 and some extent of reaction happening. So why we can find out here by let's say this reactants go away to 0. Let's say we need YNO, then this reactant is going to 0, or let's say the initial here, let's say the amount something comes because N naught, Ni naught is there. Okay, so what will happen? The total N be N1. So this be, let's say, or let's say this is 1.5 and this is half. This is half initially and this is 1 mole initially. So 1 mole and half initially. So 1 mole. Okay, plus, not plus because this is reactant. So minus 1 into epsilon. And this will be the total moles. So denominator will be same for all because this is the total initial moles plus the total. Now the total stoichiometric coefficient is minus half that we have seen. So minus half into the epsilon. Okay, so this way we can create write different y functions and finally get this epsilon. Now remember one thing, that this kp doesn't depend on this pressure. However, in equation it was p to the power v, but it doesn't depend on pressure because we have epsilon also. So if our pressure changes, epsilon will change in a way that this effect is not negligible. Okay, cancel out each other. So kp doesn't depend on the pressure. Okay, now the final thing is Van Laar equations. This is ln gamma 1 is a to the power, let's say z2 square, and ln gamma 2 is b z1 square, where z1 is equal to x1. Okay, x1 divided by x1 plus x2. Okay, this thing is like the mole fraction only. Just multiply for x2, take b first because b is second, x2 is second, b by a. Okay, and for similarly for z2 we have put this 2 1 and the opposite a by b. And one more thing is there, like how to find this a. So a you can find out ln gamma 1, okay, ln gamma 1 into something to the power square, okay. This is 1 plus, now this is 1, okay, so 1 above, so 1 down, x1 ln gamma 1, and the opposite above, okay, to the power square. This is similarly like ln gamma 1 is equal to a z square. So if this z2 square, so this divided by z2 square, so this thing kind of becomes like this. So this is the whole thing that is done here. So I hope this video will help you. Please like, share and subscribe.